understood the appendix on complex analysis, and we're ready to get into the Nyquist criterion a little bit deeper. The full Nyquist plot is the mapping of a contour gamma n that contains the right half plane and is defined as being, or beginning at the origin, moving vertically along the j omega axis to infinity, encircling the right half plane with a semicircle to negative infinity, and returning vertically to the origin as shown in figure 7.4, which is right here. So we're going to map this contour through a transfer function. Now, this contour is a little weird, right? Because first off, it's the entire imaginary axis, and it's this big semicircle, like at infinity, which is pretty freaky, but there's nothing stopping us from doing it. So that's why we did all of this work, to get to the point where we could map a contour, so we could do this step. And now, it's a lot of building up just to get to this step, but the Nyquist plot is now defined. What remains is describing the Nyquist criterion and why it works. There are several important insights required to understand it, and we're going to go through these insights one by one. But let's not lose sight of the big picture here, and that is the Nyquist plot, the full Nyquist plot, is the mapping of this contour, which is the entire right half plane contained inside of this contour, that contains the right half plane and is defined as beginning at the origin and going around the semicircle. So we need to do this mapping, and what that means, the implications of that are important. Well, I mean, what do you guys? Let's just step back right now and just think for a minute. What might it mean? It's conspicuous that we're using the right half plane, right? What happens in the right half plane that has to do with stability?
It's unstable.
Yeah, if we have closed loop poles over there, then our closed loop system is unstable, right? So that is a clue. And also, if you have something in the right half plane, and you go around a contour, the phase, if it's inside, is going to behave in a predictable manner that's different from the phase if it's outside, right? If it's outside, it's always going to move some amount back and forth, but it's never going to go around, right? If it's inside, it's going to go around. So that contribution of the phase to the mapping is dependent on whether it's inside or outside. And that's another thing that we should keep in our minds as we start to explore this. So here we go. Here's the first insight. Encirclements of the origin give us a clue. Turns out that whenever we map gamma n with a transfer function f, we find out a relationship between the number of poles inside gamma n, the number of zeros inside gamma n, and the number of counterclockwise encirclements n of the origin by the contour f of gamma n. So there's this relationship that emerges. The primary insight is that when a pole or zero is encircled by gamma n, it contributes an entire plus or minus 2 pi in phase around the contour, right? If it's inside, then it's gonna go all the way around, and you're gonna contribute either plus 2 pi or minus 2 pi. You can't help it. If it goes around you, you have to. And if you're outside, that's not true. Whereas when a pole or zero is not encircled by gamma n, its net contribution to the phase is 0, right? Because if you're outside, let's go back to our little example here. If you're outside the contour, this red line, say, it'll go up a little bit, and then it'll go down a little bit, and it'll come back up. But no matter how big that circle is, it's always going to go up a little bit, down, and then come back up, right? It's never going to go around in a complete revolution. So it's always going to have zero net effect after you go around the contour. Whereas if it's inside the contour, you're going to go all the way around and have contributed an entire 2 pi to the phase, either positive or negative. Is that clear to everyone? You go positive for a while, and then you go negative. If you're outside, you go positive for a while, then you go negative, and you undo it all, and you overdo it, and then you come back to positive, and you come back to 0. So
What do you mean by inside and outside the contour?
this is a pole inside the contour, and this is a pole outside the contour.
That contour being that circle right there?
Yeah, this is the contour. Pole outside, pole inside. Pole outside, pole outside. 0 inside. Yeah. So it just means like the normal outside and inside. Mathematically defining what inside is beyond the scope of this course. I don't want to go into that. That's the kind of stuff that I just let the mathematicians do. I like reading about it, but I don't like trying to teach it. It's not fun for me. Okay. So this yields the following relationship, which is a really simple equation that n, which is the number of counterclockwise encirclements, right? So n was here, the number of counterclockwise encirclements of the origin. P is the number of poles inside the original contour, and Z, the number of zeros inside the contour. Okay? All right. So that's a simple relationship. And this relationship is going to become a very important relationship after a few more insights. Okay? It doesn't mean a lot to us now, but it's going to become very important. So the second insight, the open loop transfer function mapping is close to what we want. Okay? So let's take a look at that. We know the poles and zeros of the of the open loop transfer function, GH, right? So, let's assume that we know them. We want to know information about the closed loop pole locations. Specifically, we're most interested in whether or not it's stable, but we're interested in other stuff too. The closed loop transfer function without compensation is G over 1 plus GH, right? Let's write G and H in terms of numerators and denominators. So G sub n is the numerator of G sub d is the denominator, and the same with H. Let's see what our closed loop transfer function looks like now. So if you combine those, and you move everything around, you see a few things that happen. So first of all, the poles of the closed loop transfer function come from both the denominator of GH and the numerator of GH, right? That's something to notice. Let's consider the denominator of equation 7.11, which is the closed loop transfer function without all of the numerator-denominator stuff in there. Okay? And we set it equal to we set it equal to this term. Let's see. Oh, we just plugged in. Sorry, just like there's a lot of terms here. So 1 plus GH, if we plug in G and H with the numerator denominator notation, we get this expression, okay? Which, combined with equation 7.12 and 7.13, allows us to see two important observations. So, first of all, the poles of 1 plus GH, which come from this, right? The denominator of 1 plus GH, equal the poles of GH, because GH, the denominator of GH, is where the poles of GH come from. So the poles of 1 plus GH equal the poles of GH. That's the first observation. The next observation is that the zeros of 1 plus GH equal the poles of T of S. Let's go back here. The zeros of 1 plus GH, which come from up here, equal the poles of T of S. So this denominator is equal to this numerator. And that's a sort of key move, because we want to know about the denominator of the closed loop transfer function. That's what we want. Turns out that that denominator shows up as the numerator of this 1 plus GH. Okay? And this 1 plus GH is much more accessible because we know GH pretty well. We know where those poles and those zeros are. So we're so close. We know the poles of GH, therefore we know the poles of 1 plus GH. We want to know the poles of T of S, which are related to the zeros of 1 plus GH, which we don't have, but we have something related. We have the open loop transfer function mapping GH of the Nyquist mapping, the right hand plane, the right half plane. Okay? All right, so a sidestep for all the money. Okay, this is our last sort of move that we have to make in our quest. So what if we just map with the open loop transfer function GH? That gives us almost exactly the same image as 1 plus GH, but shifted 1 unit to the left, right? Because we have one extra real being added to everything, so we end up shifting everything to the left. This means that if we plot GH and interpret it as 1 plus GH, we can determine stability of the closed loop transfer function. Okay? The Nyquist plot is going to be giving us information about the number of zeros of 1 plus GH show up in the right half plane, okay? And we'll see how we can understand that in a second. Let's redefine our NPZ relationship for the mapping GH. Let n be the number of counterclockwise encirclements of -1. Instead of being counterclockwise encirclements of 0, we've got this sidestep of the 1, so we have to define it to be the number of counterclockwise encirclements of -1. Let P be the number of open loop poles in the right half plane. Let Z be the number of closed loop poles in the right half plane. We want to know Z, right? That's the big one we want to know. If we have a plot of GH of gamma n, we have the first two and the third is given by the Nyquist criterion. So this is our Nyquist criterion with our redefined Z, P, and N. It allows us to find out how many right half plane closed loop poles there are, Z. So, we will use this to determine stability in lecture 7.4. However, even now, before we've really talked about stability in this much, we know that the existence of right half plane closed loop poles implies closed loop instability, right? So we can already identify that much. Before exploring stability further, we will learn to sketch the Nyquist plot, not because we don't have MATLAB, but rather to gain intuition, okay? So once again, we could just plug it into MATLAB and be done, but we're looking for intuition. So we now begin sketching Nyquist plots. Remember that we are first of all interested in the number of counterclockwise encirclements of -1, which will help us determine stability via the Nyquist criterion. We'll proceed by example. All right, I gotta get my notes for the exam. All right. So, let an open loop transfer function be defined by this. So GH is this. All right, 2 poles and no zeros. Sketch its Nyquist plot and apply the Nyquist criterion to determine the number of closed loop poles in the right half plane. So that is our goal with this problem. So first let's sketch what's going on. So we've got a make it a little bigger. So we'll sketch the complex plane, imaginary, real, and our contour. I'm going to draw this color-coded because I think it'll help. Our contour starts at the origin and it goes up to positive infinity, right? And then it goes around to, that wasn't very good. That really wasn't very good. Terrible. But anyways, it goes around to negative infinity, right? So this is infinity, this is negative infinity. And our, actually, I'm going to move this. Well, we have lots of space. You guys, don't worry, there's not like a ton of drawing here. I'm just going to move this over, though. You guys can't do that, I know. And then this last line, I'll do blue. So up to 0. So it's a closed contour. And our poles are at -7 and -4, right? Open loop poles, -7 and -4. So we have -7 and -4, not to scale. Right. So we want to know what this mapping looks like, right? That's what our Nyquist plot is going to be. And we're going to use the encirclements of -1, that's what we care about, the encirclements of -1, to go from there. So let's march along here. So the magnitude and phase of the mapped contour are, we have G of gamma n, H of gamma n. This is the mapping we want, GH of gamma n. And we want the magnitude of it is going to be equal to, you can't forget the scaling factor. So the scaling factor was 30 out here, right? So 30. And there's no zeros, right? But there are two poles. So we're going to write our sort of vector geometric one. Let's look at some point here. I'm going to label it I'm going to label a point like right here. I'll call this B. Let's call this point here C. Obviously, I need an A, which I'll put at the origin. So A, B, C. We're going to go around. This is all out at infinity too, if you're curious. Around here to this point, which I'll call D, and then back up to A. So if we're to look at just some point B along this axis, we could draw those vectors from our poles and our zeros. We only have poles in this case. And we could say this is L1, this is theta 1, this is L2, and this is theta 2. So we could say that our magnitude is going to be 30 divided by what? In terms of L1 and L2.
L1 times L2?
It's the product, right? When you're working with the magnitude, it's the product. So L1 times L2. And the phase of G of gamma n H of gamma n. Sometimes you just say like GH combined of gamma n. It's fine too. What is the phase going to be? Does the 30 affect the phase at all?
No.
No. 30. So what does affect the phase?
0 minus theta 1 plus theta 2.
Yeah, so 0 minus the quantity theta 1 plus theta 2. I'm going to say theta 1, and then I'm going to just distribute the minus sign. So the theta 1 and theta 2 are both poles, so their angle contributions are negative. Okay. So that is how we're going to want to think about this geometrically as we go from point A up to point C, around to point D. As far as we're going to think about these angles and these lengths. Okay. So let's begin at A and go up to C on the positive j omega axis. If we start at A, what are these two angles? 0 and 0, right? So I'm actually going to start drawing our map over here next to it. You can draw it, there's a lot of margin space or wherever you like. You can draw it below. I'm not going to use a lot of the space below, so you can use that below if you like. So real, imaginary. So point A maps over here zero phase, so we know that it's going to be somewhere on this real axis, right? That's where its phase is 0. And the magnitude is going to be what? 30 divided by 7 and 4, right? This is at -7, and this is at -4. So 7 times 4, 28. So 30 divided by 28 is pretty close to 1, right? So we're going to have our first point on the mapped contour. I'll make this orange because it's going to be for this segment here. Is going to be at angle 0 and magnitude of about 1. Okay. And as we move up, I'm going to actually, looking ahead, I'm going to move this out here a little bit just because I know where this is going. I want it to be scaled reasonably. And I'm going to call this point A prime, okay? The mapped A point. And as we go up this, the angles are going to do what? Right, so the angle, so these theta 1 and theta 2 increase, and since we're going up to positive infinity, they're going to approach 90 degrees, right? And it's going to get more and more vertical as we go off to infinity. So the total angle contribution after we do that is going to be -180 degrees, right? Negative pi. So we know we're going to end up somewhere over here on the negative real axis. Negative 180 degrees. It's going to swoop through this negative region because it's going from 0 to -180 degrees. And as it swoops, what's happening to the magnitude? Yeah, because these are both poles. The magnitudes of them are going to get larger and larger and larger, and they're in the denominator, so it's going to go to 0. So what we've got is this like, it's hard to draw well, but something like that, okay, where it is decreasing in magnitude and the phase is coming around to the negative real axis, okay, and then we actually approach 0, but I'm not going to draw it to 0 because you can't show what's happening when you have a point. So I'm going to enlarge the point at 0 just so we can see what happens. So we are all the way to, so this is A prime, this is C prime right here, right? So I'll just write C prime there. Maybe a little squiggle in there. C prime is in there.
C prime, did we get our angle contribution? I see how we got to 0, but then your length also, you have it hooking down and around and coming back into 0. How does that path work? Because if you go, your magnitude is the distance away, and that is slowly going back to 0.
Right.
And your angle contribution is your vertical axis.
Right.
So we went down to a certain point and then come back up. I thought we were going to 180.
Yeah, so this is 180, right? This angle. So the angle, I'll erase this, but this angle is 180 degrees. So the negative real axis is where we're going to end up. Magnitude is going to be 0. So we're coming around here, and then we're coming back, and we're going to approach this negative real axis, and we're going to approach magnitude 0 at the same time.
So you're coming back to 100 degrees, 80 degrees on the real axis, but because the magnitude is going towards 0, you can just assume that it's going to hit it. So when you graph it, you just go back in, like almost like a graph
Yeah, so it swoops around. It has a magnitude that decreases as we go.
And magnitudes from the origin.
Right, from the origin, so it's sort of sucking it in towards the origin. It's like if you had a I don't know. It's like a sink, right? It's like sucking things in and it's pulling it in. Or it's like, I know it's a good one. If you had a spool of thread and then like a ball that was on the end and it was wrapping around, it would wrap around and string would get shorter on every revolution. String would get shorter and shorter and shorter. It's doing that. That's what it's doing.
But if your magnitude starts at A prime,
Mhm.
a certain length, and then you've gone past the imaginary axis into the left-hand plane, then your magnitude has become negative, but has a quantifiable length to it.
So the magnitudes are always going to be positive, right? So magnitude is defined as the
But you would go
absolute
to
value.
and then you would hit zero, but then you would have hit zero and then gone to another positive value. That you would have a magnitude that changed from having the value, crossing zero, going back out to another length, and then coming back to zero.
We haven't had that yet, but we're going to.
Right there doesn't depict the oscillation between, because then you've gone from A, which has a length, and then you cross the imaginary axis. So once you reach the imaginary axis, so isn't that the length of zero?
No.
Or is the
So the length-
it's the ray from the origin up to this?
Right. So the length is always, so at some arbitrary point, the length is from 0 to that point.
Okay.
That's the length. So when it crosses the imaginary axis, it's some finite number.
Polar coordinate and not just the rotational ray.
Yeah. So this was the mapping of just the positive imaginary axis. And then we've got to go around the big infinity swoop, right? And that's all going to happen with these lengths L1 and L2 being infinitely large. So we're going to have zero magnitude the whole time. So we're at the origin the entire time this is happening. So we're gonna follow what the phase does, but we're not going to, and we're gonna draw it as not being a dot, but it really is just a point. So what the phase does, though, is it goes from negative 180 degrees, and it comes all the way down here to 0, right? So it goes from negative 180. It's going to be negative, but increasing to 0. So I'm going to go this way. And then it's going to continue on this region all the way to negative 180 degrees, but a minus sign on that gives you a positive 180 degrees, right? So it goes around like this. Okay? Then the arrow would go that way. Oh, we forgot to show the arrow on our orange one. So there's that. That whole infinity one just mapped to the origin. And then we've just got our point D happens, or D prime is right there. Now we've just got our blue negative imaginary axis, and it's going to go from 180 degrees, and it's going to decrease all the way to 0, right? And meanwhile, the magnitude is going to increase all the way up to, it's got to match up here, right? Started off at A, we better end up at A. So A prime, and we should end up at A prime. So we're going to be doing exactly just the opposite of what we did on the positive axis, right? It's this exact opposite. So this will look like, see if I can draw it symmetrically. It should be symmetric. Not terrible. It should look like that. And we're back at A prime. Okay? Whew! Okay, so that was our first Nyquist plot. There's a lot packed in there, right? And I want to see if there's anything else I wanted to say about that. So I'll mention two things about this. Our ad infinity little mapping, it ended up coming back to the same angle of exit as it did of entry. So this orange curve entered at negative 180 and it exited at positive 180, which is the same angle. That does not always happen, okay? Sometimes we don't exit at the same angle that we enter. However, notice that this return path here, the return stroke, the blue line, that one was symmetric. That's another observation we made, is symmetric. That does always happen, okay? The negative imaginary axis is always the same as the positive imaginary axis, but just a mirror image about the real axis, okay? So that does always happen. The Nyquist plot is always symmetric about the real axis, and the j omega axis is essentially a mirroring of the negative j omega axis. So the positive imaginary axis and the negative imaginary axis. Examining the Nyquist plot sketch, there are no counterclockwise encirclements of -1. So when we finally reach the real axis over here, so -1 we could just stick anywhere. It's out here. We never encircle it, right? And that's what we're looking to find. We're trying to find the number of encirclements of -1. From the Nyquist plot, the main takeaway for now is, in terms of stability, is how many times does it encircle -1? I'm like really interested in this. That means that n is equal to what? 0. N is the number of counterclockwise encirclements of -1. Oh, we didn't draw an arrow on our blue one, but we should have. We're looking for encirclements of -1, but we never encircled it. Therefore, n is 0. And the open loop transfer function has no poles in the right half plane, right? They were just two real poles that were both negative. So that means that P is also 0. Okay? Therefore, our Nyquist criterion just says Z equals P minus N equals 0 minus 0 equals 0. So there are no closed loop poles in the right half plane, and the closed loop system is stable. So we discovered that. Now, in this simple example, we could have simply just computed what the closed loop poles were, and we would have found out that they were stable. No problem. But we're learning a technique, and that's why we use this simple example. Yeah.
What was the condition for stability?
So Z is the number of closed loop poles in the right half plane. Yeah, and so what we do, actually, so one of the ways you can think of this as a design tool is the number of them in the right half plane. If you did get number like 2, then, so that would mean that, okay, so say you had no encirclements, n was 0, maybe you had 2 poles in the right half plane of your open loop system, so P was 2. Then you're going to have 2 so 2 minus 0, you're going to have 2 poles in the right half plane in your closed loop system. So what you would want to do is maybe redesign your system by putting in poles or zeros so that you would end up with a Nyquist plot that had 2 counterclockwise encirclements of -1, which would make n equal to 2, and then 2 minus 2 would be equal to 0, and you would stabilize the system. That's where we're headed. We're not there yet. I mean, we haven't really talked about stability with it very much, but we're just getting the basics. Yeah.
I'm just kind of shooting in the dark here, but is it like, are we going to be designing like a transformation basically for each of these complex functions to try to stabilize any instabilities? Like we always had a complex function that had some stuff in the right-hand plane. Isn't there a transformation that exists that always turns something in the right-hand plane into the left-hand plane?
Potentially. That's not the direction we're going to take it, but that is an interesting way to think about it. I don't know. I'm sure somebody's thought about it like that, or maybe they haven't. Maybe you're the first one. I don't know. But it is it's mathematically valid to think that way. I don't know if it would help us solve things in a tractable way, or maybe it would be really difficult. I don't know. It would be interesting to explore. What we're going to be thinking about is, at the first level, we'll say, okay, what happens when you put a gain in here in the closed loop? Because so far we had no compensator. So, say we had a compensator gain, what happens to this? And actually, it affects it in a predictable way, and we'll discuss that. And we can talk about ranges of gain over which you'll have stability, and when you won't have stability, and we'll see when those crossings occur. So that's where we're headed with this, but we haven't quite. We just learned how to plot the Nyquist plot. That was like our first step.
So
Okay.
the initial P would be how many times it is circled in a clockwise or counterclockwise direction. So it's not going to be done both encircled in a clockwise and counterclockwise at the
So
same time.
n is the number of encirclements of counterclockwise encirclements of -1 of the Nyquist plot. So that's why you plot the Nyquist plot, to find n. P is actually the number of open loop poles in the right half plane. So the number of open loop unstable poles that you have.
Isn't that what you said that Z is supposed to equal to?
Z is the number of closed loop. So we get to find out. So if you know the Nyquist plot and you know the open loop transfer function, you can find out stability information about the closed loop, which is what you really want to know at the end of the day is what happens to the closed loop system as a control designer. So that's why we're going through all of this, is to learn about the closed loop from the open loop. And then a plot you can construct. I mean, we plotted this. What did that take us, like 5 or 10 minutes to draw that? It wasn't too bad. It gets a lot faster. It's more akin actually to the Boda plot than to the root locus plot, although we use it more as a tool like a root locus plot than we do. But you also, so what we learn from the Nyquist plot is actually translates perfectly over to the Boda plot. And so we learn all this stuff in terms of Nyquist, but then at the end of this I'll say, oh yeah, and guess what? You can do the same thing with Boda plots. And a lot of people are more comfortable with Boda plots than Nyquist plots. Although there's really nothing, I mean, they're just different representations of the same thing, right? Magnitude and phase of the transfer function. Okay. All right. So, I was going to say a couple more things. Let's see. Yeah, there's another example that I want to do, but I think I'm going to take another break before we do that last example, that next example. We may or may not. I think we will talk about stability. I don't know if we'll get to gain margin. We'll see. All right. What if there's an open loop pole on the contour gamma n? So we didn't take that into account at all, right? So we didn't. Sorry. We're gonna take a break in a minute. Yeah, I'm just gonna. I'm setting up what we're gonna talk about when we come back. So, what happens if you have a pole on this axis? You're going to be dividing by 0 in this equation, right? And that's not cool, so we've got to figure out a way to deal with that. And so that's what we'll discuss, an example where we deal with that when we come back from the break. So